Hello and welcome to the next video in our series about Project Roscoe, which is our 68030 based computer that we're going to design, build, and hopefully it works. So today we're going to talk about a few things about the 68030. We'll look at the pinouts and what they do and what we have to do with them. And we're going to go through a couple different bus cycles that describe how the 030 talks to the world. And then we'll talk a little bit about the internal caching. So we'll start here with the 68030, the pinout. So this is a snapshot from the datasheet, and it helps us kind of get a grounding of what all the pins are and what they do. So we'll start with the sort of obvious things. So we have some address and data pins here, and notice there's 32 of the data pins and 32 of the address pins. So this gives you 4 gigabytes of addressable memory space, and you can access that in chunks of 32 bits or 4 bytes. This is about what you'd expect with this processor. But an additional thing that's a 68,000 family thing are these FC bits. And you'll see them here as FC0 to FC2. And these existed on the 68,000. And they are sort of like an extra set of address bits in some ways. They allow you to have a whole different copy of the address mapping for both user mode and supervisor mode, as well as a sort of instruction and data. And we can pull up the little chart from the data sheet. So this shows what the FC bits mean and how they translate to what the use case was. And it's an interesting thing. In the original 68,000 with no MMU, you could potentially have special memory that is in the supervisor space that doesn't exist in the user space to kind of protect them from each other. So you could use it in that way. I haven't seen really any systems that do that. It's kind of an unusual thing. I think most people just didn't use this at all, ignored it entirely. And since we have an MMU especially, you're likely to use the MMU to map what a given program can see. So we're also not going to use really any of this FC stuff, with the exception of one thing, which is this CPU space here. The CPU uses this special address space for really 2 different things that we're going to need to deal with. One is what's called interrupt acknowledgement, or INTAC, which is a process that when you signal the CPU to do an interrupt, once it sees that request, it will do a cycle called an interrupt acknowledgement cycle, where it will do a cycle into the CPU space 1, and it'll use the address bits to communicate what interrupt level it saw and it's currently going to do the processing for. And that's a way to acknowledge to the interrupt controller that, hey, I'm the CPU, I saw your interrupt, I'm acknowledging it, and I'm going to fire up that interrupt now. And so it's useful because the way the interrupt bits are done, you could possibly be signaling one and then change to another and not know which one got caught by the CPU. So this is a way for the CPU to tell you, I see interrupt level 4 and I'm executing on it now. But secondly, the CPU space is also used for the FPU. So if you have the floating point unit coprocessor installed, that is accessed in this space. So the FC bits being all 1 is used to indicate to the world, hey, I'm talking to, in this case, to the floating point unit. So we don't really need to do a lot of decoding other than that we will need to have a flag for when all 3 bits are 1, so that we know that it could be either an interrupt acknowledgement or an FPU. And those 2 are determined by some of the address bits. So there's a combination of logic. So in general, we don't need to think a lot about the FC bits other than that we'll use those to tell when we're in the interrupt acknowledgement cycle or if we're doing FPU work. So that makes it something we can mostly ignore. So let's go back to the pinout here. So there's 2 variables here called size0 and size1. And these are really interesting. And we're going to sort of cover this later when we start working on the memory interface. But the goal of the size0 and the size1 is when you combine that with address bits 0 and 1, these 4 things together allow the CPU to tell you what size of an access it's trying to do. The reason is it's a 32-bit CPU, but it could be only wanting to read or especially write only 8 bits of that 32 bits. And so these 4 together, you can build a logic table to help determine which, let's say if you have 4 SRAMs, 1 for each bank of 8 bits, which ones are enabled for a given operation. And so it's really cool. It's a neat system that is pretty easy to decode. There's a table in the datasheet that sort of explains, hey, this is how These bits map for 32-bit, 16-bit, and 8-bit access, so it's pretty easy to follow. And so when we get to the memory decoding, we'll kind of go over that in greater detail. For now, just know that we're definitely going to need to look at those bits at almost every bus cycle. There's a collection down here called the asynchronous bus control, which is all of the things used for what's called an asynchronous bus cycle. And the asynchronous bus cycle is probably the most common bus cycle that we're going to see and use. It's a way to talk to both memory and devices. It's very flexible. It allows the dynamic bus sizing feature, and it's probably what many of the CPU interfaces will use, is this method. It's a little slower. This takes a minimum of 3 clock cycles to do a complete bus cycle. It can take longer if you sort of insert wait states, but at the very fastest, it takes 3 full clock cycles to do a bus cycle. And that bus cycle could be reading a 32-bit value from memory, as an example. On the other side over here, we have the synchronous bus control. And this is the sort of other method of doing a bus cycle. And this one's interesting in that it only takes 2 cycles, so it's a faster one. It's actually very fast. And it uses just one signal called S term. And so when we get into the bus cycle definitions, we'll walk through the synchronous cycle as well. It's really meant for only very fast devices, and we're hoping we can use this with our static RAM. I think there certainly are probably many systems that have authorities that never use the synchronous bus control, because it really is a very fast cycle, and depending on how fast all your hardware is, it may be, you may have trouble keeping up. So we'll focus on the asynchronous bus control first. There's some data here about cache control, and there is one line that's really, really important, which is this C in line here. And this is cache inhibit in. And it's a signal from the outside world that you can assert when the CPU says, hey, I want to read from some address. And if you assert it, it tells the CPU, great, no problem reading from this address, but don't cache it. And that's very important, because if you're reading from a device, could be a UART or the IDE interface, many times you will read repeatedly from the same address to read in a bunch of data. And what you wouldn't want to do is to read one byte and then have that byte go into the cache, and then every time you read, it goes back to the cache, it gets the same value, it doesn't read it from the device. So it's important that we control this CI in signal so that we can tell when you access a device, tell the CPU, don't put this into the cache. Now, there is a second way to do it. In the MMU, there are flags for certain regions being non-cacheable. But in our case, it'll be easier for us to manage this by having our device logic assert this line when you talk to a device that can't be cached. So pretty easy to handle, but it's a somewhat important signal. A few other ones, the CI out just tells you if it's being cached because of the MMU table. And then this CB, ACK, and REC is for a thing called cache burst, which we'll talk about in the cache section. Up here we have the interrupt control input. So these are the things that allow you to do external interrupts. These 3 lines here, IPL 0, 1, and 2, are the lines that you pull low to tell the CPU, hey, I want to do an interrupt. And this gives you effectively 7 levels of interrupts that you can tell the interrupt controller inside the 68030 about. There's an acknowledgement one, and AVEC is a thing called auto vectoring, which is there's different ways of vectoring interrupts, and we'll kind of cover that in the interrupt controller. But these are all lines that we're going to have to interface with our interrupt controller so we can get real interrupts. The bus arbitration is a way to tell the 68000 or the 68030 to just let go of the bus and let other people use the bus. This would be commonly used for DMA applications, where if you want to have something transfer from one device to memory and have the CPU just kind of back off and leave the bus alone. So when you do a bus request and you get a bus grant back, the CPU will tri-state all of the address lines and all the other signals so that you can drive them externally to do a DMA transfer of some kind. So if we do DMA, we'll eventually need to take a look at those signals. There are some exception control signals here. Of course, reset is pretty obvious. You can use it as an incoming signal to tell the processor to reset, and also as the CPU to reset the rest of the machine. Halt and BRR are flags you can send into the CPU during a bus transaction to say something is wrong. An example is you can send both of them together to try to tell it to retry, or bus error says, hey, something's wrong. And those generally cause exceptions inside the O30 processor, so you can tell you, hey, something's wrong and we need to figure out what we're going to do about it. Lastly, we have these ones that we're certainly not going to use. They're called emulator support, and these are used for some in-circuit debugging and in-circuit emulation. So it's a way to disable the cache. And there actually is one signal, because this is the EC datasheet, there's one signal not on here called MMU disable. And these are ones we're not going to need, so we can ignore those. But this encompasses the really all the signals that we're going to need to deal with. And of course, you have the clock coming in here and power and ground. And so that kind of describes the signals. And so we'll start by looking at the asynchronous bus control, which is the one we're going to use the most. And we'll kind of look through it and understand these signals and which ones are going to be important to us and which ones are not. And now we're looking at the async bus cycle. So let's take a look here. So this is the async bus cycle as described in the datasheet. So these little numbers with the arrows allow you to go to a table to get the timing, for instance, when it starts or stops relative to a clock edge. And so we'll start at the top here. So we have, of course, the system clock or the CPU clock. And you'll notice in the motor roll timing diagrams, you can see the clock going up and down. They label each half of the clock cycle with these S's here, S0, S1, S2, and those are referred to as states. So each half a clock cycle is a state, and so the async bus cycle is a 3-cycle operation, and so it takes 3 cycles, which of course is 6 states, S0 to S5. And the use of states makes it a little bit easier to describe something in state 3 as opposed to the second falling edge after the first clock. So the use of these as a nomenclature is just an easy way to describe where you are in the bus cycle, with S0 being the first high clock part of a new bus cycle. And so we'll start with these two signals here. They're called ECS and OCS. And you'll notice these both go low here at the beginning of a cycle. And these are signals to indicate that the CPU is doing a bus cycle. The ECS is for all bus cycles, and the OCS is just for ones that are basically getting an operand, either data or instruction. And you'll notice they don't stay low. They just go low at the beginning of the cycle. And they're really useful in some maybe older designs where there were, as an example, maybe a buffer that you want to turn on that has a really long propagation delay. There are some like old transceivers where the output enable time is really long, but the flipping directions is a lot faster. And so you could use those maybe to turn one of those on since you know you're doing a bus cycle. In our use case, we really don't need these, so we're just going to ignore them. It's possible maybe in the future we come up with a reason why we'd like to have them, but in most cases we aren't going to need those signals at all. I think the single most important signal of everything on the bus is this one right here, which is AS. And the AS is the master signal that says we're doing a bus transaction, and outside world you need to pay attention. And so you see it going low right here. So this is the AS signal going low. And that tells you, as the outside of the CPU, that the address bits, the FC bits, and the size bits, they've all been set to whatever address the CPU is trying to do something with. They're all valid, and this is your time to act. So this is telling the outside world, we're doing a cycle, and you need to go look at these variables and see if you're the one who owns them, and if it is, then respond appropriately. So the AS really defines the active part of the bus cycle. So it goes low here, and you can see it goes high here. So it basically goes high in the midpoint of S5, and it goes low somewhere in S1. Now, there are a couple nuances there. The data sheet has, you can see it right here, this 9 tells you how early after the fall of the clock here that AS will be asserted, and basically guarantees you that the AS will happen sometime during S1. It depends on the clock rate, but example is at 20 megahertz, which is a 50 nanosecond clock, or a 25 nanosecond state, it guarantees to be between 3 and 20 nanoseconds after the start of the cycle. So it happens somewhere in S1, but it can be pretty close to the end of S1 or pretty close to the beginning of S1. And so just kind of keep that in mind. So the AS happens somewhere in that S1 state. There's a signal called DS, which on a read operation, it more or less follows AS. On a write operation, it happens a cycle later. And that can be useful for some devices that need the separate falling clocked edge for doing a write. But in general, most things don't need that. Most things usually pick up the thing you're writing at the end of a cycle. So we're going to nix that. We don't need that. The read-write is, of course, tells you, are we doing a read or a write? This diagram is for an async. This is a read cycle. And of course, for a read cycle, read goes to 1. And you can see that read goes to 1 before AS goes low. So when AS goes low, Read-write is another one of those signals that is guaranteed to be in its final state. So you can then decode and do whatever you need to do based off read-write plus the address, FC, and size bits. There's a variable called db-enable, which allows you to have a buffer for the data bus. And you can see it gets enabled a little bit later in the cycle. It's not really something that we need. I think there are a couple old designs that might use them, but we don't need it at all. So we can ignore that. So a lot of signals we don't need to think about. And then I think maybe the second most important signal after AS is these two signals here called the DSACK, DSAC. And I'm going to group them together, and we're going to pretend they're one signal for this conversation. We'll come back and discuss what the two of them mean, but pretend for now that's just one signal. The purpose of this signal is to tell the CPU that whatever outside resource you're calling is ready to proceed. And so when the AS line goes low, you can see it goes low here in the S1, somewhere here in S1. And then the CPU will wait, and at the end of S2, so right about here, it will go out and it will sample the DSAC lines and see if either one of them has gone low. And the idea is it's checking to see if the whatever's in the outside worlds had responded with, we're good to go. And if neither of these two lines are low, then it will insert a wait state. And when it inserts a wait state, that insertion will happen right here. You'll go from S2 to SW, and then another SW, and then it'll read again. It'll look again and see, is DSAC, either one of them, low? If it isn't, it just keeps inserting wait states, and it will do this forever. And so finally, when whatever device is ready, if it asserts one of the two DSAC lines or both, it will get caught on one of these falling edges. And as soon as it is, the CPU will proceed to state 3, then state 4, and state 5. And remember that state 5 here is when the AS line goes high. So this is sort of the end of the transaction. And so this allows an external device to insert as many wait states as it needs. So the management of these two lines is relatively important. If we have a device that can respond fast enough and doesn't need any wait states, then we can assert these lines really as soon as we detect the AS line and we decode the address. But if we need to wait, we could use one of the clocks here to create maybe a flip-flop that waits 1 or 2 or 3 clock cycles and then asserts the DSAC, and that will insert wait states. So it's a feedback mechanism that you control from the outside world. If for some reason you forget to respond to DSAC, though, keep in mind the CPU is just going to hang in a wait state forever. So it's somewhat important to have your decode logic effectively always respond to every possible address with either I'm good or this is a bad location, and you either assert error or you assert DSAC. So the reason why there are two of them, however, is because this kind of serves two purposes. One purpose is, of course, saying we're ready to go and to complete the transaction. But the second is that the 68030, it has a 32-bit data bus coming out and going in. So this is data. But the world's filled with devices, and some devices, maybe a device, could be a UART or something, that only has an 8-bit data bus. And when they made the 030, keep in mind this is 87, so a lot of devices would have been maybe 8-bit, maybe a few devices that were 16-bit devices. But there were a lot of them. So they wanted to support the idea that a device could only be an 8-bit device, but you can still hook it up to the CPU. And what happens is that when you respond with the DSX, if you respond with just 0 and leave 1 high, then that tells the CPU, hey, I'm a device, but I'm only an 8-bit device. If you respond with 1, it tells the CPU you're a 16-bit device, and you respond with both 0 and 1, then it says we're a 32-bit device. And this is called dynamic bus sizing, because it allows the outside world, every device, to individually say, hey, I can only do 8 bits. And what's really cool about the 030 is that it was done really intelligently, is that if in the CPU you were doing, I don't know, a load instruction where you're loading in a D word, so you're reading in a 32-bit value. And so that instruction executes, and it expects to go out to memory or to some device and read in 32 bits. And the device responds with, well, I'm only 8 bits wide. The CPU will automatically recognize that, and then it'll issue 4 bus cycles in a row, reading each of the 8-bit values, reassembling them into the correct 32-bit value, and then giving it to the instruction. And so the best part about this is that means you could have a flash memory or a EEPROM that is maybe your boot code or your BIOS, and it can be only 8 bits, an 8-bit wide device. And when the CPU, loads from it, it just loads 32 bits at a time, and it takes a little longer. It'll take 4 bus cycles, so it's a little slower. But it doesn't even need to know that that ROM is only an 8-bit wide device. So it's a really cool feature, and effectively means that you need in your logic to both know when to assert one or both of these, and then also which ones you should assert. So you need to know for any given device, are you an 8-bit device, a 16, or 32, and respond appropriately. And so that's really the main thing. There is one more I didn't cover here, which is RMC, which is a special flag for a read, modify, write operation. And we'll come back to that one when we're in the memory section to see how we can support that. You can choose to ignore it, and that one instruction won't work properly. So it's something we can kind of decide once we get farther along. But that describes the basics of the async cycle. As you can see, the fastest it'll be is 3 cycles. And just as a note, if we were running at 20 megahertz as an example, then each state would be 25 nanoseconds. And each full clock would be 50 nanoseconds. And if you look at the timing of when AS goes low, you're somewhere here in S1. And so maybe from around here. And here you have to say to DSAC, hey, we're good to go. And then the data is latched somewhere closer to here, right at the falling of S4. So you have 1.5 cycles. So you have 1.5 clock cycles to respond to a memory access to have basically 0 wait states. And so as an example, if it's 50 nanoseconds, that means we have 75 nanoseconds at 20 megahertz to get an answer back from a device, just to kind of give you a ballpark number. So if we had 70 nanosecond DRAM, we can probably make it work, but it'll be pretty tight because you have to include the timing delay for decoding the address bits and for setting the RAS line and having the address bits show up properly. So that might be a little tight with a 70 nanosecond DRAM. You might need 60 nanosecond DRAM to actually be able to do 0 wait states for the asynchronous. Now keep in mind, it's easy to add 1 wait state, so we can add a wait state and it'll work fine. We could add 2 wait states if we have really slow DRAM, and adding a wait state gives you a whole extra 50 nanoseconds, so it's a lot of time. So it's likely we'll not need more than 1 wait state. But again, the async cycle is really flexible. The devices can be a wide variety of speed of response, and they can all work together pretty seamlessly. And so with that in mind, we'll next go look at the synchronous bus cycle. And here we are with the synchronous bus cycle. And so we'll start up here at the top. So like the previous one, they labeled them with the S's. You'll notice it goes S0, S1, S2, S3. That's it. So this is the whole thing here. It gets done in 2 cycles. So it is in fact a fast cycle. And what you'll notice is, of course, we're going to ignore ECS and OCS, and we don't need DS. We're going to ignore that. The real key here is that you see AS going low, right around here somewhere. And the way you tell the CPU that you want to do a synchronous cycle is you assert this line called S-term. You can see it being asserted right here. And that tells the CPU, hey, we're not doing the asynchronous, we're doing the synchronous. And what you'll notice is that if you assert that S-term here, and this is, for instance, this is a read operation, so just so it's clear. So the read happens basically right here, right at the end of S2. This is when it's going to read, it's going to latch in whatever is on the data bus. And so if you get this S-term low and you get it there before this, you go into state 2, then only 1 cycle later, it will latch the data. And so you go from this point right here, sorry, not 1 cycle, 1 state. So you go from this point here to this point here, and this is when it latches the data. So you only have 1 state's worth of time before you have to have the data available. And keep in mind, we were talking earlier that at 25 megahertz, 1 state was 25 nanoseconds. So the time from when you need to do this S-term and you need to have the data available is only 25 nanoseconds. So it's very, very fast. And there's a second complication, which is that The AS line, you can see it going low here. And remember, the AS line goes low somewhere in S1. And the S term, which is what the CPU looks at to see if you're doing a synchronous cycle, it is red at the beginning of S2. So it's red right here. And you can see a problem because I'd mentioned earlier that if you look at the data sheet, when you're running at 20 megahertz, the time where AS is going to go low can be as early as just 3 nanoseconds after the start, but as late as 20. And keep in mind, this whole thing is only 25 wide. So the worst case is that AS doesn't go low until 20 nanoseconds into that cycle, which means you have 5 nanoseconds from when AS goes low to decode, figure out you want to do synchronous, assert the S term, and even worse, there's a little arrow here, the 60, is the setup time, and it's how much early before the clock goes high do you need to have S term asserted. And that is, in the case of 20 megahertz, is 4 nanoseconds. And so you can do the math, and you have a total of 1 nanosecond to decode AS, figure out it's synchronous, and assert S term. And obviously that's relatively infeasible. But the solution is that S term is a somewhat unique signal in that you can choose to make the logic for S term. So we can have a block of logic that we're going to use, and you can take the address lines and the FC lines and the size lines, and you can put those into your little bucket of logic here, and that can directly drive the S term line. And you can do it without waiting on the AS line. So normally you'd wait for the AS line to say we're doing a bus cycle, but you can ignore that and just, if you see the address that corresponds to, let's say in our case, the super fast SRAM, then you can go ahead and assert the S term. And the reason you can do that is that if you do it incorrectly, so if the address is not the right address or there's noise in the line and you glip and see that, the CPU will ignore it. It'll only look for this S term, and in the very particular case of an active bus transaction where it could be synchronous. And so it ends up that you can have this logic start as soon as the address lines get stable, and you can see those guys get stable here in S0. So you end up having almost a full, or a little bit more than a full state from when these are stable to when you need to have S term asserted. And so thus, as long as you can have this logic here be, maybe 15 to 20 nanoseconds in total time, then you'll have enough time to assert the S term. It'll be asserted here. The CPU will see it and go, okay, we're good. And just in a half a cycle or one state later, it will grab the data. So very, very, very fast. So again, keep in mind that one state is 25 nanoseconds. And we're going to know about the AS somewhere here a little bit before we go into S2. So you're going to have about 25 nanoseconds from when you know it's time to respond to when you have to have the data there. And so in our case, we're using 10 nanosecond static RAM, which gives us plenty of time to get the address there to enable the output enable, give it time to go find the address we're looking for, and put it back out on the data bus and have that data settle on the data bus for the CPU to read. And so this is certainly acceptable timing for memory this fast, but it couldn't be a lot slower. Slower than probably 15 nanoseconds, you might run into a problem where you couldn't get the data back fast enough. But it is a really cool way because it's very fast, only 2 total CPU cycles to do a full bus cycle and to read 32 bits. This only works, by the way, with 32-bit devices. So there's no, like with the previous async, there were the 2 DS ACKs and you could use them to encode how big of a device. This only works at 32 bits. So it's really meant for very fast memory. Similar to the previous one, there's a line here called CIIN, which is that cache inline. And again, if you're a device, you can choose to assert that and say, hey, I'm a device, don't cache any of this. I think typically you wouldn't often have devices that are this fast, so this is probably not going to get used a lot. But it's a good transaction. And if, by the way, for some reason, this logic is a little slow and you miss the window for the S term, then the CPU will just add a wait state and then look again. And so in some ways, you could choose to use S term, be a little bit late, and then do an extra cycle. At that point, then you're now doing a 3 bus cycle, at which point you probably should have just done the async one. There's not a huge amount of advantage of doing it this way. but it is possible. So if your design was for some reason tight in some way, the way the logic works, there's not a lot of risk to it. If for some reason you're a little bit late, or if the CPU, when it asserts is late for some reason, then you'll add an extra wait state, which you would probably not notice that much. And so this is a great way, if you can get it into your design, to do a very fast cycle if you have a fast enough device and fast enough memory. So that's the synchronous bus cycle. And this video is going to be pretty long, so we're going to wrap this video up. And in the next video, we're going to talk a little bit about the caching in the 68030, both how it works and a few of the quirks. It's a slightly quirky cache, and it's worth understanding that as we sort of get into the design element. So that's it for this episode. Thanks.